Hey guys, welcome into Chapter 3. Title of Chapter 3 is Derivatives, and we're going to begin with Section 3.1, which is Derivative of a Function. Okay, so here's what we are going to be looking at in Section 3.1. First, we're going to define the derivative. Then we're going to talk about two different types of notation, Newton versus Leibniz. We are going to see the relationship between the graph of our original function and f prime, which is the derivative of that function. We're also going to try to graph the derivative from some data, and we're going to look at one-sided derivatives. Okay, so before we get started and jump into the new stuff, we're going to go back and talk about secant versus tangent. So we're going to use this function, x squared plus 2. We're going to look at the interval from 1 to 3, and we're going to find the slope of the secant line there. So let's get our points in. There's point P at 1, 3, and point Q up here at 3, 11. And here's our yellow secant line drawn in. And we're going to try to find the slope of this secant line. So there's our slope formula, change in y over change in x. So let's see. We're going to have, what do we have here? 11 for my change in y. Let me get my pen out here and going. Okay, so our change in our y values would be 11 minus 3 over our change in x values, 3 minus 1. So we're going to get a slope of 8 halves, or 4 for the slope of that secant line. So that means that the average rate of change from a to b, from x equals 1 to x equals 3, for this function was 4. An average rate of change is just the slope of the secant line over those endpoints of the interval a to b. So that's how we find average rate of change over a certain time period. What we also looked at the end of Chapter 2 was instantaneous rate of change, and this would be maybe change on just one day instead of looking over that range of days from 1 day to 3 days. Let's look at just change on one day, which would be the tangent. So we started with a secant through P, and then we chose a point Q that was very near to P, and we found the limit as that point Q approached point P. So here we go. It says find the slope of the tangent line of f of x equals x squared plus 2 at the particular point where x equals negative 1. Okay, so we're using our limit definition here. We're finding the slope of the tangent. So we're going to put in f of x plus h. So our x value is negative 1. So right here is the expression for negative 1, f of negative 1 plus h, minus f of negative 1 would be right here, all over our h value. This 2 plus h minus 2 is going to be our h value. Okay, so let's get started here. We're going to do some algebra. Negative 1 plus h, that quantity squared, we're going to get, let's see, 1 minus 2h plus h squared there, plus 2, minus, and then let's see here, our f of negative 1 value, well, negative 1 squared is 1 plus 2, so we're going to be subtracting 3 there, all over our denominator of h. So let's see, some simplification here. Well, our 1 plus 2 is going to cancel with that minus 3, so we're going to have negative 2h plus h squared left on the top, which, as typical, we're going to factor out that h, so we're going to end up with h times negative 2 plus h over our h value, and just like we liked, our h is going to cancel out, and now the limit of this as h approaches 0 is negative 2. So that means that at the particular point when x is equal to negative 1, the slope of that curve is going to be negative 2. Okay, so now we're ready for definition of derivative. Derivative is nothing more than the slope of the tangent line at a particular point. So this right here is going to be how we're going to define derivative. And notation of derivative is f prime. This little prime means the derivative of the function f. And that's going to be the limit as h approaches 0 of f of a plus h minus f of a all over h, just like we've always done in the past. That should look very, very familiar to you. Whoops, I got some red ink there we don't need. And this, of course, only works when the limit exists at that given particular point or that given a value. And these are a lot of things that the derivative will do for us. It gives us instantaneous rate of change, and it also gives us the slope of the graph at that particular point. So many thanks to the derivatives. It's very useful, and there are lots of different things we're going to use it for. Okay, so we are going to differentiate f of x equals x cubed. Differentiate means find the derivative of. So we are going to go ahead and use our derivative definition. So we are going to do f of a plus h minus f of a all over h. Let's see here. I'm going to get rid of that. I got some stray stuff there. Let's get rid of that ink. There we go. Okay. Alright, so f of a plus h into x cubed. So we are going to do a plus h, that quantity cubed, minus f of a would be a cubed over h. Okay, we need to find the quantity a plus h cubed. A couple of different ways we can do this. We can certainly change this to a plus h, the quantity squared, times a plus h. We can FOIL that out and then multiply through. Another method, if you're not familiar with doing this, is using Pascal's triangle. And we are doing a third power, so I'm going to use the third row of Pascal's triangle here. So let's see, we have our 1, 1, and then our second row would be 1, 2, 1. So our third row of Pascal's triangle, 1, 3, 3, 1. And this is for cubic expansion. And what this tells us, these are the coefficients of our terms. And we have decreasing powers of the first variable. So we're going to have decreasing powers of a and increasing powers of h. So we're going to start with our first coefficient of 1. So we're going to have a cubed. Next term is going to be 3. And then our powers of a decrease while our powers of h increase. So we're going to go from a cubed down to a squared, and from h to the 0 power here up to h to the first. Okay, plus, next we have another 3, so we're going to again decrease power of a, increase power of h, and then lastly, coefficient of 1 will decrease our power of a again is going to be 1, so just increase power of h brings that up to h cubed. So there's our expansion of a plus h, the quantity cubed. Alright, minus our a cubed for our f of a value up there in the numerator. All of that over h. And let's see, we're going to get some cancellation happening here. A cubed and minus a cubed are going to cancel there. And then when you look at this expression that's left in the numerator, h, 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 so we have an h to cancel out, which is always what happens. So we have our 3a squared plus 3a h plus h squared, all of that over h. Cancel off our h's, of course, and we are taking the limit as h approaches 0. So this term is going to zero out, that term is going to zero out, and our slope is going to equal 3a squared. Anywhere that we are on this curve, the slope at any particular point is going to be 3 times that point squared. That is the derivative, or the slope at any particular a value, tangent to that curve x cubed. Okay, here's a different definition we can use. Instead of using a small value like h approaching 0, we're going to force x to approach a, where x and a are the same thing. Well, if x approaches a and x and a are the same thing, that's definitely going to be pretty small. We're going to be looking at a difference of 0 between our 2 points. So here is an alternate definition for derivative. The derivative at any particular point a is going to be the limit as x approaches a of f of x minus f of a over x minus a. And the advantage to this is it oftentimes makes our algebra a lot easier to deal with. So here's an example that we're going to use this alternative definition of derivative for. So we're going to look at the function f of x equals the square root of x, and we're going to use our alternative definition for the derivative. So we're going to start with f of x minus f of a. Well, if f of x is the square root of x, so we're going to have square root of x minus f of a would be square root of a. All of that is over x minus a. Okay, and we have to find a way to do some algebra to make this a little bit better to work with. And we have square roots here, which is often indicative that we need to multiply by the conjugate. So the conjugate of the numerator is going to be square root of x plus the square root of a. We're going to multiply by that unit fraction. And when we do that, very nicely, our numerator is going to change to x minus a. And our denominator, let's see, we have this x minus a over there. And then we're multiplying by that quantity, the square root of x plus the square root of a. So what we have is cancellation of those terms, leaving us with 1 up there in the numerator. So if we are taking the limit as x is approaching a of 1 over square root x plus square root a, in place of x we're going to substitute a. So we're going to get 1 over the square root of a plus the square root of a, which is 1 over 2 square root a. And this, I think you're going to find this definition of derivative oftentimes to be less clunky than the x plus h minus f of x over the h value to use. So just an alternative way with a little bit easier algebra to do.